physical properties of the universe prior to what's called the inflationary epoch.
So you're saying for the pendulum in that epoch, we can't, because you can infer things about the pendulum before you showed up to the room in our current epoch, correct?
Right. Yeah, so if you look at it right now, but if I said, well, when will it stop oscillating? So that depends on how much energy it got initially, and you can measure its dissipation, its air resistance. You had infrared camera, you can see it's getting hotter maybe, and you could do some calculations. But to know the two things in physics to solve a partial differential equation, the initial conditions and the boundary conditions. Boundary conditions were here on Earth and gravitational exclusions wildly beyond length of pendulum. It has simple properties. But this is like, in other words, you can't tell me, when did the solar system start in the way that it does? In other words, when did the that's a pedestrian example. But what I'm telling you is that the inflationary epoch purports and is successful at providing a lot of explanations for how the universe evolved after inflation took place and ended. But it's nothing.
Trying to say
the point. And that's really what you're asking. I mean,
you're lucky that they kept you.
Fusion reactors and the whole universe of fusion reactors, but don't you really care about what happened at the first moment of time? And the problem is we can't really answer that in the context of the Big Bang. We can't answer that in the context of the alternatives. You have to go from the alternatives. So one is aeon theory, which comes from the cyclic cosmology. Another one that's was really popular in the 60s and 70s until the discovery of the primary component of my research field, the cosmic microwave background radiation, or CMB, the 3 Kelvin all-pervasive signal. Solved the death knell, in some sense, to what was called the quasi-steady state. And then there was another model that kind of came out of that. You hear the word quasi, so it's not steady state. Steady state is always existed. That was the cosmology Einstein believed until Hubble showed him evidence for the expansion of the universe. And most scientists believed in that for millennia, basically. The universe was eternal, static. They couldn't believe that after Hubble, so they had to append onto it, concatenate this new feature that it wasn't steady, it was quasi-steady. So the universe was making a certain amount of hydrogen every century in a given volume of space. And that amount of hydrogen that was produced was constant. But because it was producing more and more every century, the centuries pile up and the volume piles up, the universe could expand. And so that's how they developed.
But slowly.
Very slowly. And it doesn't match observational evidence. So that is...
By the way, did I think...
I would assume that he thought it was infinite because there was really, if something had a no beginning in time, or it has, in that case, a finite edge to it. The silly joke was that there are only two things that are infinite, the universe and human stupidity, and I'm not sure about the universe. So.
Well, me saying I'm not aware of the joke is a good example of the joke. It's very meta. Okay, so, all right, so sorry, you were saying about quasi, all the alternatives in quasi-steady state.
And the most kind of promising, although I hate to say that, people say, what's your favorite, alternative, right?
This is not investment advice.
Inflation is not transitory, it is quasi-permanent. So a very prominent...
Sorry to interrupt, we're talking about cosmic inflation, so calm down, cryptocurrency folks.
Although the first Nobel Prize, and one of the first Nobel Prizes in economics was awarded for inflation, not the cosmological kind. So most people don't know that inflation's already won a Nobel Prize.
It's a good topic to work on if you want a Nobel Prize. It doesn't matter the field.
Exactly.
Buddy?
So when we look at the alternatives called bouncing or cyclic cosmologies, these have serious virtues, according to some. One of the virtues to me, just as a human, I'm speaking as a human, one of the founders of the new version of the cyclic cosmology called the bouncing cosmology is Paul Steinhardt. He's the Einstein Professor of Natural Sciences at Princeton University. You've heard of it. And he was one of the originators of what was called New Inflation. In other words, he was one of the founding fathers of inflation, who now not only has no belief or support for inflation, He actively claims that inflation is baroque, pernicious, dangerous, malevolent, not to science, not just to cosmology, but to society. So here's a man who created a theory that captivated the world of universal cosmologists such as it is.
How'd you get up?
This theory was and now he's like, I joke, I'm like, oh, you're denying paternity. He's like, you're like a deadbeat dad. Now you're saying like,
Fuck. I'm so sorry.
but he doesn't just attack. See, this
That
is
was
what's
the
very
end of
important
you.
about
Yep, that's
things that are experimental. He's got a lot of theorists on, and that's one thing. An experimental
out.
he or she has no confidence that they will there if I could rewrite it until they need one, right? Garbage. But it's vital. Fuck yourself! Completely kind of unpersuaded by the beauty and the magnificence and the symmetry and the simplicity of some idea. Like inflation is a beautiful idea, but it also has consequences. And what Paul claims, I don't agree with him fully on this point, is that those consequences are dangerous because they lead to things like the multiverse, which is outside the purview of science. And in that sense, I can see support for what he does, but none of that detracts from his fact. But man, imagine like, Elon comes up with this like really great idea, space, and then he's like, oh, actually, it's not going to work. But like, here's this better idea, and he's like, SpaceX is not going to work, but he's now created an alternative to it. It's extremely hard to do what Paul's done. Doesn't mean it's right. Doesn't mean I'm gonna like have more and more attention paid to it because he's my friend or because I respect the idea or I respect the man and his colleague Anna Aegis, who works really hard with him. But nevertheless, this has certain attractions to it. And what it does most and foremost is that it removes the quantum gravity aspect from cosmology. So it takes away 50% of the motivation for a theory of quantum gravity. You've talked a lot about quantum gravity. You talk to people and people on the show. Always latent in those conversations is sort of the theological expectation that there is a theory of everything. There is a theory of quantum gravity, but there's no law that says we have to have a theory of quantum gravity.
So that kind of implicit expectation has to do ultimately with the inflationary theory, so in cosmic inflation. So is that at the core? So okay, maybe you can speak to what is the negative impacts on society from believing in cosmic inflation.
So one of the more kind of robust predictions of inflation, according to its other two patriarchs, considered to be the patriarchs, Alan Guth at MIT and at Stanford, was that the universe has to eventually get into a quantum state. It has to exist in Hilbert space and Hilbert space. And then it becomes very difficult to turn inflation off. So inflation can get started, but then it's like one of SpaceX rockets. It's hard to turn off a solid rocket booster, right? It continues the thrusting, and you need another mechanism to douse the flames of the inflationary expansion, which means that if inflation kicks off somewhere, it will kick off potentially everywhere at all times, including now, spawning an ever-increasing set of universes. Some will die stillborn, some will continue and flourish, and this is known as the multiverse paradigm. It's a seemingly robust consequence, not only of inflationary cosmology, but more and more we're seeing it in string theory as well. So that sometimes two branches coming to the same conclusion is taken as evidence for its reality.
So one of the negative consequences is it creates phenomena that we can't, that are outside the reach of experimental science?
Yeah.
Or is it that the multiverse somehow has a philosophical negative effect on humanity? Like it makes us, maybe it makes life seem more meaningless? Is that where he's getting at a little bit? Or is it not reaching that far?
Well, no, I think those are both kind of perceptive. The answer is a little of both, because in one sense, it's meant kind of to explain this fine-tuning problem that we find ourselves in a universe that's particularly fecund. It has features consistent with our existence, and how could we be otherwise? The sort of weak anthropic principle. On the other hand, it a theory that predicts everything, literally everything, can be said to predict nothing. Like if I say, Lex, you've been working out, you look like, you have been, it's great. You're, about somewhere under 10,000 kilograms. Like, all right, yeah, you're right, but that's hardly imprecise. So what good is that? That's meaningless. I don't contribute any what's called surprise or reduction in entropy or reduction of your ignorance about this. You know exactly how much you. So me telling you that tells me nothing. In this case, it's basically saying that we're living in a universe because the overwhelming odds of our existence that we would exist. There has to be at least one place that we exist. But the problem is, it's a manifestation of infinity. So humans, and I'm sure you know this from your work with AI and ML and everything else, that humans, as far as we know, really are the only entity capable of contemplating infinity. And we do so very imperfectly. So if I say to you, like, what's bigger, the number of water molecules in this thing or the number of real numbers? Or if I say what's bigger, the number of real numbers or rational numbers? They're all different classifications of the amount of infinities that there could be. Infinity to the infinity power, kids someday, I love you infinity, you have to come back, I love you infinity plus one, right? So, but the human brain can't really contemplate infinity. Let me illustrate that. They say in the singularity, the universe had an infinite temperature, right? So, let me ask you a question. Is there anything that you can contemplate in the Einstein's little clip aside, infinite, like a physical property, pressure, temperature, energy, that's infinite? And if you can think of such thing, I'd like to know it. But if you can, how does it go to infinity minus one? The opposite direction I go with my kids. How does it go from to half of infinity? Because that's still infinity. How did it cool down? How did it get more and more tenuous and rarefied? So now it's only infinity over 2 in terms of pascals.
Less infinite, more infinite. Yeah, I mean, it's that's one of the biggest troubling things to me about infinity is you can't truly hold it inside our minds. It's a mathematical construct that doesn't. It feels like intuition fails, but nevertheless we use it nonchalantly, and then use like physicists. They're incredible intuition machines, and then they'll play with this infinity as if they can play with it on the level of intuition as opposed to on the level of math. Maybe it's something cyclical. You can imagine infinity just going around the same, kind of like a Mobius strip situation. But then the question then arises: how do you make it more or less infinite? All of that intuition fails completely.
And I mean, how do you represent it in a computer, right? It's either some placeholder for infinity, or it's 1 divided by the smallest, possible, real number that you can represent in the memory.
Well, that's basically my undergraduate study in computer science is how to represent a floating point in a computer. I think I took 7 courses on this topic. It was very useful.
So I came to the right place. But in terms of what a physicist will mean, you're right. I mean, physicists will blithely, nonchalantly subtract infinity, renormalization, and do things to get finite answers. And but at a certain point, you have what are the consequences for the real world? So one of them, you ask, what's the problem? Does it make it more meaningless? Many of the people that support it, like Andre Linde. Andre Linde says, you have a bias. You believe in a universe, but shouldn't you believe? What evidence do you have that there's not? So he turns it around. Whereas Paul Steinhardt will say, no, if anything can happen, then there's no predictive power within the theory. Because you can always say, well, this value of the inflationary field did not produce sufficient gravitational wave energy for us to detect it with BICEP or Simon's observatory or whatever. But that doesn't mean that inflation didn't happen. And that's logically 100% correct. But it's like kind of chewing, Wonder Bread. I apologize if they're one of your sponsors, but
Wonder Bread /Lex.com.
Type in code CLEB, right? It's my CLEB. It's my favorite Russian word. Is like, would you like a piece of CLEB?
By the way, even that word CLEB, which means bread in Russian, as you say it, like you're jokingly saying it now, it made me hungry because it made me remember how much I loved bread when I was in the Soviet Union. When you were like hungry, that was the things you dreamed about. I don't know.
What's amazing is how many of the Soviet scientists contributed to so much of what we understand today. And they were completely in hiding. Like, there's no Google. They couldn't look up on Scholar. They had nothing. They had to wait for journals to get approved by the Communist Party. And then then and only then if they weren't a member of some class. I'm sure you know, like Jewish scientists, you had a passport that said Jew on your passport. And Zeldovich, the famous Yaakov Borisovich Zeldovich, he was the advisor, one of my advisors, Alexander Polnareff. And he had to, not only because he was like at a Nobel level and he was one of the fathers of the Soviet atomic bomb, could he even get his Jewish student, he was Jewish too, but only by virtue of his standing of his intellectual competence would they give him the dispensation to let his student, travel to Georgia or something. And it makes what we complain about. I complain about academia, and it's like, they were able to create things like inflation, completely isolated from the West. I mean, some of these people didn't meet like people like Stephen Hawking. He was almost dead.
How you fallen.
And they just learned this thing through smuggled in. It's a work of heroism, especially in cosmology. There's so many cosmologists that work incredibly hard, probably because they were working they could pass off as, well, we're doing stuff for the atomic. They wouldn't.
At the same time, there is interesting incentives in the Soviet system that maybe we can take this tangent for a brief moment. That because there's a dictatorship, authoritarian regime throughout the history of the 20th century for the Soviet Union, science was prioritized. And because the state prioritized it, news and so on, and beneficial to society because you were seen as a hero, as there's
Stalin was hero of the Soviet Republic.
And that, there's positives to that. I mean, I'm not saying I would take the negatives with the positives, but it is interesting to see a world. It's just the American system. The celebrities are the athletes, the actors and actresses, maybe business leaders, musicians, and the people we elect are lawyers.
Right.
So it's interesting to think of a world where science is highly prized, but they had to do that science within the constraints of always having Big Brother watching. It's,
the same in Germany. Germany had highly prized. One of the most famous cases Fritz Haber invented the Haber-Bosch process that allowed us to. I don't know. Have you eaten yet? You look. I mean, I know you fast, intermittent fast every day, and you do that. I said glad, and you got a little bit.
He says I'm lifting and I look slim. This is amazing. I'm going to clip this out and put it on Tinder. I think that's what.
You got to swipe left or right for that. I don't know. But when you think about what he did and created the fertilizer process that we all enjoy and we eat every day, he was a German nationalist first and foremost, even though he was a Jew. And he personally went to witness the application of ammonia chlorine gas applied during trench warfare in 1960. Go and witness these atrocities, but above, I don't want to say human dignity, but of the fact that he would later be suppressed, and actually some of his relatives would die in Auschwitz because of the chemical that he invented also called Zyklon B. And so it's just unbelievable. So I feel like that does have resonance today in this worship of
There's that.
I always say, just because you're an atheist doesn't mean you don't have a religion. Just because you in my case, in my books, I talk a lot about the Nobel Prize. It's kind of like a kosher idol. It's something that you can worship. It doesn't do any harm. Intellectual accomplishments, because there is a core of America and the Western world in general that does worship and really look at science, predominantly because it gets technology. But there's something really cool. But also recognizing how much good, maybe all.
You open so many doors because you also bring up our Ernest Becker in that book, So there's a lot of elements of religiosity to science and to the Nobel Prize. It's fascinating to explore, and we will. And we still haven't finished the discussion of the beginning of the universe, which we'll return to. But now, since you opened the book, wow, pun unintended, of losing the Nobel Prize, can you tell me the story of BICEP, the background imaging of cosmic extragalactic polarization experiment, BICEP 1 and BICEP 2, and then maybe we can talk about BICEP 3. But the thing that you cover in your book, the human story of it. What happened?
Yeah, that book is in contradistinction to the second book. That's like a memoir. It's really a description of what it's like to feel, what it feels like to be a scientist, and to come up with the ignorance, uncertainty, imposter syndrome, which I cover in the later book in more detail. But to really feel like you're doing something, and it's all you think about. It is all consuming, and it's something I couldn't have done now because I have too many other, wonderful, delightful demands on my time. But back to that moment when I was first captivated by the night sky as a 12-year-old, 13-year-old, and really mixed together throughout my scientific story has always been wanting to approach the greatest mystery of all, which I think is the existence or non-existence of God. So I call myself a practicing agnostic. In other words, I do things that religious people do, and I don't do things that atheist people do. And I once had this conversation, with my first podcast guest, actually. I was just having a conversation with Freeman Dyson. But he was actually my first guest. And I miss him.
Name drop.
Name drop, yes. I'm sure there's going to be plenty of comments about
So in case people don't know, Brian Keating. So when I talked to Freeman, I said, Freeman, you call yourself an agnostic too. Can you tell me something like what do you do on Sundays? Do you go to church? It's like, no, I don't go to church. And I'm like, well, imagine there was like an intelligent alien, and he was looking down, or she was I don't know. Thing was looking down, and it saw Freeman. And on Sundays, like a group of people go to church, but Freeman doesn't go to church. And then there's another group of people who don't go to church, and those are called atheists. But Freeman calls himself. He does the things that Richard Dawkins. He doesn't go to the same church that Richard Dawkins doesn't go to, right? So I said, how would you distinguish yourself if not practice? So I'm a behaviorist. I believe you can change your mentality. You can influence your mind via your bodily physical actions. So when I was a 12-year-old, I got my first telescope. I was actually an altar. It's kind of strange for a Jewish kid who grew up in New York. We'll get into that. But I was fascinated by these. For a second.
Okay, yeah. All right, let's go.
Let's go there. Let's go to Baby Brian, or Young Brian.
The new sitcom on CBS. Young Brian, born to two Jewish parents. My father was a professor at SUNY Stony Brook. He was a mathematician, eminent mathematician. And my mother was an eminent mom and brilliant English major, etc. And they raised us, but they were secular. They we'd go to. I always joke. We'd go to synagogue, 3 times a year. Christmas and Easter. No, we would go, Yom Kippur, Rosh Hashanah, right? That's and we'd have matzahs once a year on Passover, and that was about it. And for years I was like that until my parents got divorced. My mother remarried, and she married an Irish Catholic man by the name of Ray Keating. My father's name is James X. So when she remarried Ray Keating, I was immediately adopted. I'm actually adopted into the Keating family. And he had 9 brothers and sisters, and just warm and gregarious. They, did Christmas and Easter. It was one of the most wonderful experiences I had. And I do things with great gusto. Whatever I do, I want to take it all the way. So to me, that meant really learning about Christianity, in this case, Catholicism. So I was baptized, confirmed, and I said, I want to go all the way. An altar boy.
You're going to be the best altar boy there ever was.
I had serious skills. You passed that collection basket. I could push people and get them to 2x their contributions. But in this case, I was 13. I don't know if you remember, when you were 13. But if you extrapolate the next level up, the graduate student, postdoc, the next level up from confirmation, altar boy is priest. And I don't know if you're aware of this, but priests are not entitled to have relations with him. And as a 13-year-old boy, kind of like future casting what life's going to be like for myself if I continue on my path, I found it. Maybe I.
The math did not up.
That's right. There was a serious gap in that future. And instead, when I
I've
could have
got
been
so
preparing
much
for my
ammo
bar
with
mitzvah, as most Jewish boys would be,
I need to
12,
stop.
13-year-old boy.
I do this
I actually
every
got a
time I play
telescope
first person. I conserve
and
my
became
ammo
infatuated with all
when
things
I
you could see
shoot,
with it.
and then I
It's
end up
bigger than
taking
that one over
like
there that your
5 times
hedgehog's
as long
looking
to
through.
play the game.
Is that hedgehog?
It's a hedgehog in the fog. I should mention, and we'll go one by one these things. You've given me some incredible gifts. Maybe this is a good place to ask about the telescope that put some clamps on the hedgehog look. And using...
Now you're officially an experimental astrophysicist. You assembled
Becky!
this telescope,
Hi!
you gave it a mount, and you connected it to a very
Yeah, but
powerful...
there's no experiment going on. It's just engineering for show.
are you?
Okay. It's very shallow. It's
So-
experimenters taking it to the next level and actually achieving something. Here, I just built a thing for show.
Well, that's always a joke. People say, "Oh, you're an experimental cosmologist." I'm like, "Yeah, I build a lot of universes." Actually, most of my time is putting clamps on things, soldering things. It's not actually doing the stroking of my non-existent beard, contemplating the cyclic versus the bouncing cosmological model.
Yeah,
Right?
and just like most of robotics is just using Velcro for things.
Right, yeah. It's not like having dancing dogs and whatever, right? So, telescope.
Yes, this telescope. What's the story of this little telescope?
This telescope's a very precious thing in some ways, a symbol of what got me into, what brought me all the blessings I have in my life. Came from a telescope. And I always advise parents or even people for themselves. You right here, wherever we are, the biggest city on earth, Manhattan, where I was growing up as a 12-year-old outside of Manhattan. You can see the exact same craters on the moon, the same rings of Saturn, the same moons of Jupiter, the same phases of Venus. You can see the Andromeda Galaxy, Lex, 2.5 million light years away from Earth. You can do that with that little thing over there. Or one that's a little more expensive. Get one that has a mount, and you can attach now your smartphone. What the hell is that? I wouldn't have known what that was in 1984. And with that, you can do something that, to my knowledge, can really replicate. You can experience the physical sensation that Galileo experienced when he turned a telescope like that to Jupiter and saw these 4 dots around it. Or that Saturn had ears, as he called it. Or that the moon was not crystalline, polished, smooth, and made of this heavenly substance, the quintessence substance, right? So where else can you be with the first person? Try doing that with the Higgs boson. Get yourself an LHC and smash together, high luminosity, call up Harry Cliff, and say, I want to replicate. How did you feel? He didn't feel anything. None of them felt anything. It took years to compile it. You can't do it. But with this, you can feel the exact same emotions.
That's fascinating. It's almost like maybe there's another one like that is fire.
Yes.
Like when you build a bonfire, like can you actually get it? See, if you use a lighter, I think if you actually, by rubbing sticks together or however you do it without any of the modern tools, that's probably what that's like.
Yeah.
And then you get to experience the magic of it, of what like early humans. By the way, is this a gift?
This is the gift.
Okay.
You need a little bit of a swag upgrade, so I got you some.
Yeah, this is I'm pulling a Putin. Like, asked if this is a gift, making it very uncomfortable for you to say. Not really.
This is actually my childhood telescope here.
But now I'm keeping it.
That's
all
right.
right.
So looking through this telescope
was when your love for
Changed
science was first born.
changed my life because not only was I doing that, I was replicating what Galileo did. But I was, I'm 100% not comparing myself to Galileo, okay, if there's any confusion out there. But I did replicate exactly what he did, and I was like, holy crap, this is weird. Let me write it down. So it had another effect, which all good scientists, budding scientists should do, and all parents should do. Get your kid a book, a little notebook, tape a pencil to it. Write down what you see, what you hypothesize, what you think it's going to be. Not like in the high school, hypothesis, thesis, but just like, wow, how did I feel? Better yet, astronomy is a visual science. Sketch what you see. The Lagoon Nebula, the Pleiades 7 Sisters. You can see them anywhere on Earth. And when you do that, again, you're connecting 2 different hemispheres of your brain. And you're connecting them through your fingertips. You literally have the knowledge in your fingertips, in your connection between what you see, what you observe, and what you write down. Then you do research, right? The goal of science is not to just replicate what other people did, is do something new. And that's what we call research, and not just like studying, Wikipedia. And in so doing, you start to train a kid at age 12 or 13 for $50. It's unbelievable. And now we can do even better because you got to share it on Instagram or whatever. And you can, by doing so, have an entree into the world of what does it really mean to be a scientist, and do so viscerally. I often say, I was taught this by my English teacher, Mrs. Tompkins, in 9th grade, that the word educate, it doesn't mean to pour into. Let me pour in some facts, intellects, and it's not like machine learning that you're showing like billions of cats, or you're not like forcing it in, you're bringing it out. It means to pour out of in educare. And what more could a teacher want than to have something that the kid is just like gushing? No, you're not going to see like
To inspire the kid.
Yes.
Inspire. Yeah. Shout out to Mrs. Tompkins.
Yeah, Mrs. Tompkins. She's awesome. She's a big fan. Me, she doesn't care for, but you.
Yeah, excellent. We take those we love for granted. This is in Manhattan.
This is in Westchester County, New York.
Okay, got it. But then that's where the dream is born.
Yeah.
But then there is the pragmatic journey of a scientist. So going to university, graduate school, postdoc, and all the way to where you are today. What's that? What are some notable moments in that journey?
So I call that the academic Hunger Games, because it's like you're competing against like these people, who are just getting smarter all the time as you're getting smarter all the time. They want to get into a fewer and fewer number of slots. Like there's fewer slots to get into college than in high school. There's fewer slots in graduate school. There's very fewer slots to be a postdoc, and many, maybe infinitesimal number. We just did a faculty search at UC San Diego, 400 applicants for one position. It's almost getting impossible. Like I almost can't conceive of doing what these new brilliant young people applying to become an assistant professor at a state university that they're doing. Like it takes so much courage to do that. So I went from this kid in New York thinking I would never be a professional astronomer. A, because I didn't know any, I'd never seen any. I didn't even know that they existed. And I thought, who the hell's going to pay me to look at the stars? Like, will they pay me to be like an ice cream taster? Like, it's just not something I could conceive of getting paid to do, even if I had the brilliance to do it, which I didn't feel I did. And then I went to graduate school. And during graduate school, I had this kind of on-again, off-again relationship with my father. And I knew that he was a mathematician. He had left and got remarried himself and moved across the country. I didn't see him for 15 years. And in that time, I learned a lot about him, and I learned that he had gotten very interested not in pure mathematics, but he had been a number theorist and contributed to seminal work on the Fantine equations, played a role in Turing's work. But anyway, he had become interested, turned completely away from that into the foundations of quantum mechanics and relativity, which was physics. And by that time, I was at Brown University, and I was thinking, maybe I'll be a matter physicist or experimentalist. I never thought I'd be a theorist, and I'm not a theorist, so it was pretty prescient. And but it always appealed to me as like, why not do what made me happy as a 12-year-old? Like, we often forget about like those primitive things about us are probably the most sustainable, durable, and resilient attributes of character. So with my own kids, I look like, what are they interested in now when they're young? And it doesn't mean that's what they're going to do. I mean, some of them want to play Fortnite, like professional Fortnite play, which there are. But, the odds of that is less than the odds of being a professor.
Can I ask you, is your father still with us?
No.
Just in a small thing, do you miss him? Do you think about him? Does his mathematical journey reverberate through who you are?
Oh, yeah, absolutely. I mean, it did in very many ways. And he's been gone for a long time now. Thinking back to that time with him, he must have instilled some capacity for me to only want to spend my time, which is a limited quantity. I don't think it's the most limited quantity. Maybe we'll talk about that later. But to go into only the most challenging, interesting things with the limited time that we have while we're alive. And for him, it was the foundations of quantum mechanics. For me, it was the foundations of the universe. And how did it come to be? And I felt like, well, people have been trying since Einstein to outdo Einstein, really haven't made great progress in the foundations of quantum mechanics. But this is an exciting time. The Kobe satellite had just released its data that the universe had this anisotropy pattern. Stephen Hawking called it like looking at the face of God and so forth. And so it seemed like this is a good golden age for what I'm going to do and what I'm most interested in. But always throughout that, I wanted to understand. I didn't want to be a wrench monkey. No offense to people that just do experiment.
And no offense to monkeys.
But thinking back to what animates me, it's not doing the engineering as much as it is getting the data. But there's a lot of steps. I want to be the guy understanding what made the universe produce the signals. So I always joke with my theorist friends who call me a closet theory. You know, it's like I want to be, you know what they call a guy who hangs out with musicians, a drummer. So I want to be like,
fuck off,
physics, right? Like, for theoretical physics. I want to be like the guy who doesn't do new theory, but understands the theory that the new theorists are doing.
I love that formulation of a theorist is understanding the source of the signal you're getting. Like the signal is primary. Like the thing you measure is primary, and theory, the search of explaining how that signal originated, but it's all about the signal. I mean, I see the same shit in your mind, and like neuroscience in that same kind of way. It's ultimately about the signal, but you kind of hope to understand how that signal originated. That's fascinating.
Man,
that's such a beautiful way
think this game would be a little easier, but
to explain
I'm
experimental physics, because it ultimately at the end of the day is all about the signal.
Yeah, and maybe those two things, the neuroscience and the cosmos, not getting too romantic, but yeah, maybe they're linked in some fundamental way. Maybe they're some fundamental cosmic consciousness. But
we're gonna get to that.
Yeah, no, we definitely have to get to that. But getting back to so my origin story. So I always say, like, and I want to try this on you. You said you wouldn't answer any of my questions, but I'm going to ask you some questions. What's the most important day on the calendar? Don't tell me the date, but what's the most important day to you every year?
Do I have to answer or do I have to think about it?
No, just answer. Like, you don't have to tell me the exact date of the calendar. It could be like your mistress's, birthday or whatever. But
I have so many I lose track. Even though I'm single, how does that even make sense?
I know.
Okay, I'm sorry. So a day, like a month and a day. Yeah, I mean, for me, it would be December 31st.
Yeah. So I was going to say New Year's Eve, New Year's Day. Some people say birthday, anniversary, kid's birth. They're usually signifying beginnings and ends, right? January means the portal between the God was the portal between the beginning and the end. So you're looking back, maybe because you're Russian, like the death side, the light side, looking forward to January, the beginning, right? So everybody's most important day is usually some beginning or something significant. For me, it was studying the most significant thing of all. It was like, when did the universe get born, as I said before? And I didn't think there was some mental obstruction that I didn't realize that I could get past, because I didn't think like anybody does it. Like, I knew astronomers knew these answers, like the universe at that time between 10 and 20 billion years old. Now we know it's 13.872 billion years old. It's incredible, the 5-digit, per significant.
What is it again?
13.872 billion years. 872 million.
So is there a lot of plus or minus on that? What are the error bars on that?
For me, I'm 50. So it would be the equivalent of you looking at me and telling me within 12 hours how old I am.
Yeah.
So 0.5% level accuracy.
There's a confidence behind that?
Oh, yeah. I mean, there's the significance. Yeah. No, it's extremely well measured. I mean, it's one of the most precise things that we have. In contrast to, again, 25 years ago, we didn't know if the universe was 10 billion or 20 billion years old, but there were stars in our galaxy that were believed to be, as they are, about 12 billion years old, or in the universe that were 12 billion. So that would be like you being older than your father. It was embarrassing.
Can we actually take a tangent on a tangent on a tangent on a tangent? How old is the universe? Can you dig in onto this number? How do we know currently with those, I guess you said 4 or 5 significant digits?
So we can come about it from two different ways. Well, basically, they rely on the most important number in cosmology, which is called the Hubble constant. The Hubble constant is this weird number that has the following units. It has the units of kilometers per second per megaparsec. So it's a speed per distance, which means you multiply it by distance and you get a speed. And what is the speed you're measuring? Well, you're measuring the speed of a distant galaxy at many megaparsecs away. So a galaxy at 1 megaparsec away, this isn't actually strictly true because of local gravitational effects. But if you go out, say, 1 megaparsec away, I'd say that galaxy is moving 72 kilometers per second away from you. And every galaxy, except for the very most local group surrounding us, maybe a half a dozen galaxies, out of 500 billion galaxies to perhaps a trillion galaxies. So 12 out of that number are moving towards us, the rest are moving away from us. So that number, if you invert it, if you say, well, when did those things last touch each other, all those galaxies? Now they're really far apart. We know how fast they're moving away. It's a very simple algebra problem to solve. When were they touching? That's where you get that number from.
So there's the local 12 and then the rest.
Ignore the 12, yeah.
And then ignore the 12 and then look at the others and then solve the algebra problem. How does the stuff in the beginning, the mystery of that beginning epoch change this calculation of?
Very little, because actually we understand how there's some other ingredients that go into it, namely how much dark energy there is in the universe, how much dark matter there is in the universe, how much radiation, light, neutrinos, etc. there are, and how much ordinary matter, like we're made up of, neutrons, protons, croutons.
Okay, so
morons.
It appears that the universe is bigger than it is older. How does that make sense?
Yeah, so you're talking about the fact that we can actually see stuff in our observable universe that's located at a distance that is farther than the speed of light times the age of the universe.
Yeah.
Naively, you would say that So you're right. If the universe were static, if the universe came into existence, and you can conceive of this, the universe came into a big bang in a fixed universe. So the universe just started off. Those galaxies were, they could be moving towards us, away from us, who knows? That you could say, I can see a galaxy that's at a distance of only 13.8 billion years times the speed of light. That would be true. But the fact that the light is expanding along with the expansion of the universe. So imagine there was some very distant past, we were near a galaxy. It's going to produce some light. And that galaxy is going to be moving away from us. The light's going to be getting more and more red shifted, as it's called. And it's going to be moving farther and farther away from us as time goes on. There'll be some acceleration as we get into the era of dark energy. The light signals, there'll be some cone of acceptance, if you will, from which represents all the events that we could have received information from. We can't currently communicate with that galaxy. It sent us some light, and now it's moving away, and it sent us some light. And because the space is also dragging the photons with it, if you like, the photons are being participating in the expansion of the universe. That's why they're redshifting. That we can see things out to where the universe first began expanding, not just when it began existing. And because the universe has been expanding for 13.8 billion years with no sign of slowing down yet, which is a huge surprise, serendipitous surprise, that we can see things approximately 3 times the age of the universe away from us. So we can see this called the age of the universe 15 billion years, just to make the math simple. We see things at 45 billion light years distance in that direction. And we see things at 45 billion light years in that direction, just turning our telescopes 180 degrees away. So that means we see things that themselves are 90 billion light years away from each other. That's sort of the diameter of the observable universe. Is there another universe beyond that? We don't know. So conjecture, there's not only one, there's an infinite number of them.
How are you emotionally okay with the fact that our universe is expanding? So
it's going to be like Annie Hall, like with Alvy Singer.
I'll grow up in the Soviet Union. We watch propaganda.
I realized that you did, yeah. So there's a famous...
Annie Hall? Is that some kind of... What is the...
propagandist movie with Woody Allen. Certainly canceled, but nevertheless, back when he was not canceled yet, he made a movie called Annie Hall, in which, it's a self-depiction. He's like a Larry David before Larry David was Larry David. Typical neurotic young Jew. He's in Brooklyn, and he all of a sudden tells his mother he's not doing his homework anymore. He refuses to do his homework. His mother says, why? He goes, because the universe is expanding. And it keeps on expanding, everything will rip apart, and then we'll never have anything in contact, and everything is meaningless. And I assume these are some of the topics we're going to get to. And she goes, what are you talking about? We're in Brooklyn. Brooklyn is not expanding. And that's true. Brooklyn is not expanding. The solar system is not expanding. Oftentimes they get asked, what is the universe expanding into? That's one of my favorites. What is it expanding into? And I say, it's actually an easy question if you think about it. You've seen your friend Elon. He goes out in space. He's got a rocket, right? What's outside of the rocket? If you take this bottle, empty out this bottle, take the cap off it, go outside the rocket, sip in some Tang, screw on the cover of it. What's in there? Is it empty?
That's just semantics, I guess. Yeah.
No, it's definitely not empty.
So you step outside the rocket,
Yeah, you're in the vacuum of space, the quote-unquote vacuum of space.
and there's no more liquid in it.
There's no more liquid in it. No, it's just a container, 1 cubic centimeter. Let's just make it simple. 1 cubic centimeter of a box, and you take it out into space outside the Falcon, whatever, right? What's inside that box? It's not empty. There's actually, I'm gonna say, this is gonna set your. There's 420 photons from the fusion of the light elements that we call the cosmic microwave background inside the box at any second.
Okay. All right. Hold on a second. What? 420. That's I've heard of that number before. All right.
It used to be 69, but then they changed it.
Wow, physics works in mysterious ways.
In the millimeter box, it's 69.
What are we talking about here? What's in what's in the box?
I'm gonna get it. That's right. Let's think outside the box. No, we're thinking inside the box. So if you have every cubic centimeter of our observable universe is suffused with heat left over from the Big Bang, dark matter particles. There's a little ordinary matter in the universe. And every cubic centimeter, there's some probability to find a proton, a cosmic ray, an electron, etc. There's actually an awful lot of neutrinos inside of that cubic centimeter. Now, just imagine how many cubic centimeters there are in the universe. It's enormous. That's why there's enormous numbers of particles in our universe. It's a very rich universe. But now let's zoom in on that box. So now inside that box, there might be, one, let's say there might be one ordinary matter, like a proton or an electron, a baryon, a lepton. There might be a couple hundred neutrinos, and there'll be a couple hundred photons, as I said, 420. What's between those guys? What's between the protons and the neutrinos and the photons? Like, just zoom into a cubic micron now. Like, imagine 420 things inside a box this big. It's actually pretty empty. Like, they're just zipping around in there, right? So between them, there's a lot of empty space.
And this is outside the kind of physics-based models of fields and all those kinds of things. Just actually asking the question of, like, what is this emptiness?
What's the particle content in the universe in every cubic centimeter of the universe?
Outside of the 420. So you have the 420.
420.
They have some, they have some mass.
Yeah. Oh, they have energy. They don't have mass. Photons don't have mass.
Energy.
That's why they don't bring suitcases. You know that's true, right? Photons never bring suitcases with them, because they're traveling light. See, I don't even get a laugh out of you. That's corny dad jokes. Okay, you'll appreciate something.
No, this is pretty good. It's just I'm laughing on the insides. What's in the box? What's the 420? What's between the photons?
That's what space is. That's what the universe is expanding into.
Okay, that's the notebook on which the photons are written. That's
beautiful.
But still, thank you. Still, I understand this, but it's still uncomfortable that if the universe is expanding, that this thing is expanding. The canvas is expanding. It's very strange. Because like if we're just sitting there still, I guess if we're in Brooklyn, nothing's expanding. So our cognition, our intuition about the world is based on this local fact that we don't get to experience this kind of expansion.
Yeah, and that intuition leads us astray. But you know that gravity is the weakest of the so-called four fundamental forces. And yet it has the longest range pervasiveness. Gravity is, we're being pulled towards the Andromeda Galaxy at some enormous rate of speed because of its massive counter-gravitational force, the force we exert on it. So gravity is enormously long range, but incredibly weak. And because of that, we can think about these effects of expansion as the relationship between as you said, the grid lines on the notebook, right? Gravity is a manifestation of the interrelationship between those points, how far they are from each other, and those can change. Those point distances can change over time. that we didn't need this enormous Hubble telescope. We didn't need a 30-meter diameter telescope. We needed a tiny refracting telescope, no bigger than my head, less than a foot across. And that telescope would he was like this. I don't know.
Where were we?
He's like an Steve Jobs or Elon, charismatic, handsome, persuasive, idea man. Not the guy always in the lab doing everything, but understood where things are going decades ago. And he had been involved in an experiment that actually measured the universe was flat, very close to flat, along with a preceding experiment done at Princeton by Lyon Page and whatever.
So the shape of the universe is flat.
The geometry of the universe is flat.
How did he do that experiment?
So he used the cosmic microwave background. And so what I said is you have to look for triangles in the universe. So you can measure triangles on Earth. You can actually, it's hard to show the Earth is curved, but you can show the Earth is curved using triangles, mountaintops, etc. If you have an accurate enough protractor.
Allegedly, yeah.
God, you're like auto-canceling. This is great. My ratings are going to go up, man. This is going to be great.
If you want actual science, go listen to Brian. If you want all of these conspiracy theories, or AKA the truth about flat Earth, listen to him.
So what he used was the following triangle. There are proto-galaxy-sized objects in the CMB. The cosmic microwave background has these patches, and so you can make a triangle out of the diameter of one of these blobs of primordial plasma, the soup that constitutes the early universe. It's just hydrogen. It's very simple material. Understand hydrogen, electrons, and radiation. Very simple. Plasma physicist, son, understand it. The diameter is one base of the triangle, and then the distance to the Earth is the other two. So he measured, along with his colleagues at Caltech and University of Rome and other groups at Princeton, measured the angle, interior angle, effectively, very, very accurately, and showed that it added up to 180 degrees.
Can you localize accurately the patches in the CMB? Can you know where they trace them back location-wise?
You can know where they are, but more than that, there's so many of these patches. They're about 1 square degree on the sky. the sky, you may know, a sphere has about 44,000 square degrees in a sphere. So there's literally 44,000 of these size patches over which he could do these kind of measurements to build up very good statistics. That's not exactly how they do it or how they did it in this experiment called Boomerang, but they did measure very accurately the what was called the first Doppler peak or acoustic peak in the plasma, the primordial plasma.
That's fast. So the sphere has approximately 44,000 square degrees. So to cover a sphere, that's a very kind of important data collection thing when you're sitting on a sphere and you're looking out into the observable universe. So there's a lot of patches to work with.
Yeah. And in fact, a lot of the fast kind of algorithmic decomposition of spheres and machine learning in the early 2000s, still used today, was created out of this field by data analysts using this thing called hierarchical equal area triangles called heel picks is what it's called.
And so just stitch all this stuff together, and that's you can stitch it together very accurately.
You get high statistical significance in order to reduce the statistical errors. Very clean signal and measurement device to reduce the systematic errors. Those are the two predominant sources of error in any measurement. Those that can be improved by more and more measurement. You take more and more measurements of this table, you'll get slightly better each time, but you only win as the number of the 1 over the square root of the number of measurements. But the square root of 44,000 is pretty big. So they were able to get a very accurate measurement. Again, it's not exactly how they did it. They also have to do a Fourier analysis, decompose that, do a power spectrum, filtration, windows. There's a lot of work that goes into it. Image analysis, and then comparing that with the cosmological parameters. It's a very simple model, just 6 different numbers that go into the model to make a prediction. And one of those is the geometry of the universe pops out. And that is the universe has 0 spatial curvature. And that was called Boomerang. So he had just come off of this. Now, let me remind you, who was the first person, to measure the curvature of the Earth? It's a guy named Aristophanes in the, whatever, lived around Aristotle's time. His name is in the history book. So this guy, Andrew Lang, I was like, he's like the next Aristophanes. Like, I just wanted to work for this guy. He was clearly had this brand. He was about 40 at the time. California Scientist of the Year. I was sure he was going to win a Nobel Prize for that. And I knew that he, so I went down to Caltech to get this job. And he said, I love it. You got a job. And before I could even, before he finished the sentence, I said, I'll take it. It was too good. And I started working there at Caltech, and slowly but surely, because Caltech's a rich private university, at that time run by a Nobel Prize winner by the name of David Baltimore, he just wrote us a check. Baltimore wrote us a check and said, get started on this idea. And so we started coming up with the idea for what I later named BICEP, Background Imaging Cosmic Extragalactic Polarization, which is kind of ironic because we ended up measuring galactic polarization. We'll get to that in a minute. But along the way, the idea was very simple. We're going to make the simplest telescope you can possibly make, which is a refracting telescope. Your eyes, you have 2 refracting telescopes in your head. Only way, forward is making things more complex, right? And when you make things complex in science, you introduce the possibility for systematic errors. And so we wanted to build the cleanest instrument. It turns out the cleanest instrument you can build in astronomy is a refracting telescope. We also had to, unlike that telescope or Galileo's, we had to use very sensitive detectors that were cooled less than 1/20th of the temperature of the cosmic background itself, which is the coolest temperature in the whole universe. So we had to cool these down to about 0.1 or 0.2 degrees Kelvin above absolute zero. To do that, we needed to put it inside of a huge vacuum chamber and suck out all the air molecules and water molecules and take it to a very, very special place called the South Pole, Antarctica, from which we retrieved for you a patch that is over there. So when you go in there, you get these bright red jackets.
Right? Oh, yeah.
You fly down.
As somebody was born in the Soviet Union, we obviously like the color red. United States Antarctic Program, the National Science Foundation.
Man, you can die no matter what.
The Amundsen Scott South Polar Station. So it's a little known fact of geopolitics that whatever country occupies a region has ownership over it.
All right, you guys.
Now, there is a treaty in Antarctica. You can't use it for
go
military purposes, for mining, et cetera, et cetera. But I don't know if you know, but about 12 years ago, Putin sent a submarine to the North Pole. There's no land